Good afternoon, class. So, for today's section, we want to get started in Chapter 4. And so we're covering chapter sections 4.1a and 4.1b in this video. So what's the big deal here? Well, in the end of the previous chapter, we started talking about what are absolute maximum, what's an absolute minimum, what is the first derivative test, and how can we use the first derivative test to tell us more about our function. Well, today the big highlight is the second derivative test. And yes, as the name indicates, we're going to be using the second derivative. But first, let's talk about that. What is a second derivative? Because up to this point, and this is 4.1a, up to this point, all we've done are first derivatives, which just means if I give you some function, say x cubed plus x squared, then we could take the derivative, which is shown by f prime, and that's just 3x squared plus 2x using our power rule. The second derivative is when you take the derivative again. So this is, we'll write notationally as f double prime. So I'll just have two little prime symbols up there. So f double prime of x is equal to, and I'll just do the derivative a second time based off of the first derivative. So I'll have 3 times 2, that's 6x plus 2. And now I have a second derivative. So with that being said, what does that really mean? What does that tell us about derivatives? So when you have a function, this firstly tells us that you can take the derivative as many times as you like. Now eventually you might end up just hitting 0, and so you've got nothing new. So in this case, if I take the third derivative, then that would just be 6. And then if I take the fourth derivative, then that would just be 0. And then after that, the derivative of 0 is just 0. So there's nothing really interesting beyond the fourth derivative here. Point being, whenever I give you a function, you can take the derivative as many times as you'd like. Sometimes that can be useful, especially if you have a really high power function. In this case, it's x cubed, so it doesn't take long before the derivatives down below don't give us as much information. But if like it were x to the 5th, x to the 7th, x to the 12th, then in that case, a lot of these other derivatives might be more helpful and might be more interesting. So there you go, that's what a second derivative is. But now let's talk about why do we care about the second derivative. And that's where the second derivative test comes into play. So what is this test? So what we have here is, so just a brief definition, and we just talked about this. So the second derivative is the derivative of the first derivative. So maybe that definition is kind of like, well, duh, of course it's what it is. But in the case where maybe you hadn't seen the second derivative before, it's nice to write out in plain English. So there we have it. Now, what do we have here? What's going on here? Well, and you know what? Actually, I misspoke. The second derivative test, we're actually going to touch on in 4.1b. So that's still going to be in this chapter section. It's still going to be 4.1, but not in 4.1a. So we'll get there to the test, but not yet. We got some definitions to cover with the second derivative first. Right. So why do we care about the second derivative? Well, if f double prime, so the second derivative of a, so some value where x equals a, if the second derivative is greater than 0, then f is concave up at x equals a. Now let me stop there for a moment. What does concave up mean? Well, let me give you an example first. If we have, let's see. Well, that doesn't fit that definition in that case. Well, yeah, we'll make it work. Okay, so if we have the function, and I think we saw this in the previous video. So if f of x is equal to, let's say, x cubed plus, not 2, plus 3x squared. Well, this was that graph we had where we had a 0 at 0, but then it was also 0 at -3, and it looked something like this, right? We had a graph that looked like this. So to relate to what is concavity, what does it mean to be concave up? Well, for that we need the second derivative. So I'm going to write f prime here. F prime of x is equal to 3x squared plus 6x. But then f double prime, that's 6x plus 6. So this is equal to 0. And so 6x is equal to -6. X equals -1. So I'm going to create a number line using the second derivative, and this will be important for determining what is called concavity. And again, we're going to touch on that again here in a second so you know what concavity actually means in terms of a picture. So we have this -1 point where it's 0. And just as before, I'm just going to pick numbers to the left and right. So f double prime of 0 is going to be a 6. So that's positive. Over here to the left, if I plug in -2, then f double prime of -2, it's going to be -12 plus 6, it's going to be -6. So that's negative. So what does that mean? Well, based on my definition here, I'm saying for any a value where the second derivative is positive, where it's bigger than 0, then my graph is concave up. So I'm saying for any of these x values, and here if I've got -1 written, then for all my x values to the left of it, it's concave up, which concave up, when you're looking at your f graph, to be concave up just means that you're in a portion of the graph where it's curving upward. So it could make a U shape. It could also be like maybe you're curving upward like this. What have you, whether it's this kind of U shape or like this guy. In either case, the idea of concave up means you kind of have this curve going upward. In other words, you kind of have like a bowl shape. So what I often tell students is when you're looking at a graph and maybe you're just given a picture, so maybe you have a picture that looks like this, kind of like the graph we have over to the left here. Whenever a question is asking you, where is the function concave up? Then instead ask yourself, if I were to pour water over the function, then where would the water fill up? Where would the water be able to pool without spilling off? Well, here where I have this bowl shape, it can hold water. So basically, one way to think about it is, if the function can hold water at that point, then it's concave up. It makes a bowl shape. So that's what it means to be concave up on the right side of this function here, which then means as the definition might suggest, that there is such a thing as concave down. And this is going to occur if your second derivative is negative, less than 0, then f is concave down at x equals a. And what does it mean to be concave down? That means you've got like an upside down U shape. It's like an upside down bowl. If I were to pour water over it, it would not hold water. It would just pour off. And from this example here, we saw that it was negative for values of x less than -1. And that we can kind of see from the picture here, because from here downwards, the curve is shaped downward. And so we call this concave down. Okay, so that's all fine and good. We can use the second derivative to tell us about concavity. But why do we care about concavity? Well, as we'll see in 4.1b, it does become useful in the second derivative test, but we're not quite there yet. And we'll actually probably come back to that same example I just erased, but oh well, we'll come back to it. So, what's next? Well, next we have another definition. This guy is called point of inflection. Point of inflection. Now, what is a point of inflection? A point of inflection occurs where at C in the domain of f, so I'm looking at a particular x value. So it occurs where at C in the domain of f, the concavity changes from positive to negative to the left and right of C, or vice versa. It could be changing from negative to positive. Whichever the case is, the point is that to the left and right of this value C, the concavity is changing signs. So what else does that tell you? Well, that also tells you in order for the concavity to change signs, in order for it to switch from negative to positive or from positive to negative, that means that the value at C had to equal 0. Or it had to be undefined. Which goes back to our definition for critical points. If you recall, a critical point is where the first derivative is 0 or undefined. And so in this case here, we're looking at the second derivative, but it's still just important. If we're trying to locate these points where concavity changes sign, then we have to look for where the second derivative is 0 or undefined. So more specifically, this leads us to our next definition. If f double prime, if the second derivative at C is 0 or undefined, then C is what we call a hypercritical value, or you could call it hypercritical point. Point being here, this is very much like our definition for a critical point, except for a critical point we were talking about where for a critical point we were talking about where the first derivative is 0 or undefined. A hypercritical point It's the same kind of idea, except for the second derivative. So what else do we have here? Well, and as I kind of hinted at down here, all points of inflection are hypercritical points. All points of inflection are hypercritical points, but not all hypercritical points are points of inflection. Why is that? Well, it's possible that when I draw my number line for the second derivative, maybe I'll have some point where it's 0. So this is C. And so this C is a hypercritical point by the definition up here. However, maybe to the left and right, it's positive on both sides. So the graph is concave up on both sides. And so the concavity did not change on either side of this hypercritical point. And so it is not a point of inflection. So points of inflection are hypercritical points, but hypercritical points are not necessarily points of inflection. So it's an important thing to test when you draw out your number lines to make sure that, yes, indeed, this is a point of inflection. So it's a good thing to point out and a good thing to remember as we work through some of these examples. All right, so that covers our definitions for 4.1a. So let's go ahead and apply them and see kind of how they work out here. Alrighty. Okay, so example 1. Let's let f of x equal 1/3 x cubed minus 2x squared, 2x squared plus x minus 3. And suppose the question asks, find where the function is concave up or down. So find concavity. So what is concavity? It's all about the second derivative. So that's exactly what we're going to do here. So we take our first derivative. F prime of x is equal to 3 times a third is 1. So we have x squared minus 2 times 2 is 4. Power decreases by 1. We have 4x plus derivative of x is just 1. And then there we go. There's our first derivative. Now, what else does this tell us? Well, if we were to set this equal to 0, then we could find our critical points. But at the moment, we're not trying to find our critical points. So we're going to go ahead and take our second derivative. So what do we get for this? The 2 comes down, so we have 2x minus 4. And there we go. There's our second derivative. Now to find our hypercritical points, we have to set this equal to 0. So I set it equal to 0, and I've got 2x is equal to 4, x equals 2, and so this is my hypercritical point. That's my hypercritical point here. And so now I draw my number line just like I would for the first derivative, and I label my hypercritical point. So I have x equals 2. At that point, the second derivative was 0, and now I need to test both sides. So f double prime of 3 is 3 times 2 is 6, minus 4, that's a positive 2, so it's positive. And then if I plug in 0 on the other side, so f double prime of 0, that's 0 minus 4, that's a negative 4, it's negative. And so what do I know? Well, now I know, remember the sign tells you if it's up or down. So if it's left side, from negative infinity up until 2, f is concave down. And for the right side, from 2 on upwards to infinity, f is concave up. And that's it, we're done. So in a lot of ways, these concavity questions are very much the exact same questions we were doing before, where you are trying to find your first and second derivative. This is the same deal, except now we're taking the second derivative, setting the second derivative equal to 0, and then testing values on different sides to fill in this number line. This is the second derivative, which is one way to find concavity, and this number line specifically is what we're going to use extensively when we start to talk about the second derivative test. So in order to get into that, let's go ahead and switch gears to 4.1b, and we'll get to the punchline of today's section, of today's lecture. So 4.1b. 4.1b. Let me switch pages over here. All right, so this is the second derivative test. So the second derivative test, first we have to let f be twice differentiable. Why do we care about that? Well, you have to be able to take the derivative twice before you can use the second derivative test. If you can't take the derivative 2 times, then the second derivative test doesn't apply because it requires the second derivative as per the name. So, okay, we're assuming we can take the derivative twice. All right, good. That's all fine. Now what? Well, suppose we have a point where f double prime, the second derivative, is equal to 0. In other words, we're talking about these hypercritical points. So if we have a hypercritical point, then 1, if f, or I'm sorry, I misspoke. Not the second derivative. Hold on, let me back up. I misspoke for that definition. Let f be twice differentiable, because we need to be able to take the derivative twice. Then, suppose f prime, so only the first derivative, not the second derivative. Suppose f prime, the first derivative of c, is equal to 0. Then, what does this test say? So this test, it's not talking about hypercritical points. It's talking about critical points where the first derivative is equal to 0. So find your critical points and then test your critical points with your second derivative. So we're looking at points where the first derivative is equal to 0. Then 1, if the second derivative at that point is greater than 0, it's positive, then C is a local min. Why is that? Well, again, so recall that local minimums and local maximums occur where we have critical points. So critical points are candidates for local mins and maxes. We know that's required in order to have a local min or max. But why does the second derivative give us this information that we automatically know it's a local min? Well, think about it. First, suppose we have some point. So here's our point C. And then suppose it's got a slope of 0. That's what it means to be a critical point. Okay, so we have this point, and it has a slope of 0. This is the dotted line indicating slope. And then we suppose that its second derivative is greater than 0. What does that mean? What does that tell us? Well, that tells us that the function is concave up. And remember, what does concave up mean? It means that the function is curving upwards. So if we're curving upwards at this point where the derivative is 0, then to the left, we have to be curving upwards. That's what it means to be concave up. And to the right, now maybe it's happening very slowly, but it has to be curving up at least a little bit in order for it to be concave up, in order for the second derivative to be positive. But what have I just drawn? I've drawn a situation where this value of C is smaller than the y values to the left and right, because to the left and right it has to be curving upwards. Otherwise, the second derivative would not be positive. So this is a very nifty trick. You can use the second derivative to actually tell us where our local min and local max are. And as we saw at the end of 3.5, if you know where local minimum and maximum are, then you know where possible absolute max and min are. So this is very good. This is very helpful. Just like the first derivative test tells us where possible local min and max are, the second derivative test also tells us about local min and max. Okay, so let's keep going. So we talked about if it's positive. Then we have case 2. If the second derivative at that point is less than 0, so it's negative, it's concave down, it has to be curving downwards to the left and right of that point, then C is a local max. So this is great. We can find our local mins, we can find our local maxes based off of what sign the second derivative takes at that point. But this test requires that we're testing points where the first derivative is equal to 0. So we're specifically checking the critical points for the function. And then our third case, what if neither happens? What if f double prime equals 0? Then what can we say? Well, in that case, then unfortunately, the test is inconclusive. If we have something where the second derivative is 0, then it doesn't actually tell us anything about the local min or max. Why is that? Well, again, and going back to 3.5, I believe we talked about the examples where f of x equals x squared. Then in this case, we had the just standard parabola U-shape. Note that we have an absolute minimum here at 0. This is also a local minimum. So we have a critical point at c equals 0. But if I take my second derivative, so my first derivative is 2x and then my second derivative, oh, you know what? Actually, this doesn't help us here. Bad example. Let me back up. Bad example. Sorry about that, everybody. Instead think about, suppose we have the example, let's think about this instead. if f of x equals x, then what do we have? Well, then f prime is equal to 1. F double prime, what's the derivative of a constant number? Is 0. We have a constant for our first derivative, and so when we take the second derivative, we end up with a value of 0. So what do we have going on here? Well, if we're picking, and you know what, that's not a good example either, because this test is supposed to only look at C that are critical points. So that's a bad one too. Actually, you know what, let me pause this for a second and make a good example, and then we'll talk about it. Alright, and I'm back. Apologize for that. Unfortunately, that's just the way of mathematics. Sometimes you get an idea and you gotta play with it for a moment until you see what you're trying to do. But now we're good to go. We have an example we can work with. So what do I have here? So let's suppose f of x is equal to x cubed, so that's x to the third power, divided by 6, minus x squared divided by 2 plus 1/2 times x. Now this is going to be a case where we're going to have a critical point, and then when we check the second derivative at that critical point, we're going to get 0, and it's not really going to tell us much of anything. So here we go. So f prime, the first derivative, is equal to 3 comes down. 3 divided by 6 is 1/2. Then we have x raised to the second power. And then 2 comes down over here. 2 divided by 2 is just 1. So I've got a negative x, and then plus 1/2 on the end. So there's my first derivative. Now the first part of this test says, suppose f prime of c is 0. In other words, the possible c that we're testing for have to be critical points. So let's go ahead and find my critical point. So I set this equal to 0, and I'm going to multiply this equation by 2 on both sides of the equal sign, just so that I can get rid of these fractions. So I multiply it by 2, and I'm going to have x squared minus 2x plus 1 is equal to 0. But if I factor that, that's x minus 1 times x minus 1. So I have a critical point at x equals 1. Okay, so here's my c. This is my candidate I want to test on. And let's take my second derivative. So the second derivative here, the second derivative of x is equal to 2 times 1/2 is 1. So I've got x to the first power. And then the derivative of negative x is just negative 1. But now when I plug in c, or in this case, when c is 1, then I have 1 minus 1 is 0. My second derivative is 0. So in this case, is it a maximum? Is it a local maximum, or is it a local minimum? Or is it maybe nothing at all? Well, to figure that out, let's go back to the first derivative test. What does this tell us? Well, based on the first derivative, and I draw my number line again, I'm looking at 1. If I plug in numbers to the left, so let's say 0, then f prime of 0 is equal to a positive 1/2. So I got a positive here on the right. And if I plug in f prime of, let's say 2, then I'm going to have 2 squared is 4. 4 divided by 2 is 2. 2 minus 2 is 0. And then when I add a half back, I get a positive 1/2. So it's positive again. So what is this? Well, recall that a local maximum or a local minimum occurs when the slope, when the first derivative changes signs. But here, I just having something that's increasing, increasing, increasing. It flattens out, and then it starts increasing again. So this is not a local max or a local minimum. And so in this case, when you have a second derivative of a critical point, and the second derivative of your critical point is 0, then this test is inconclusive. It doesn't tell you anything about the local max or min. You're going to have to use some other test to figure out what's going on here. And this is an example of why the second derivative doesn't help in this case. So, good thing to keep in mind. And this also, with our previous example up here, when the second derivative is positive or negative, then this second derivative test can tell you a lot of information about where our local mins and local maxes are. Okay, so this is good. What's next? What's next? We've covered the second derivative test. Which is just this guy we have written here. This is the second derivative test. Okay, so now what? Well, now we'd like to talk about, so another business term here. So, and this is our last vocabulary term for this section. So, the point at which sales, so we're talking about business here. So the point at which sales continue to increase. So this is where sales continue to increase, but at a slower rate. So what does that tell us? Well, that tells us we're already told sales are increasing. So that's our first derivative. It has a positive slope. It's increasing. But the rate at which it's increasing, it's at a slower rate. So it's increasing at a slower rate than it used to be. Well, a rate is also a derivative, right? It's a rate of change. But we're looking at the rate of change of the rate at which we're increasing. So we're looking at a rate of a rate. Well, what is that? That's what we call the second derivative. So this statement is telling us that f prime, the first derivative, is increasing. It's positive, but it's increasing at a slower rate. The rate at which it's increasing is decreasing. And so our second derivative is negative. All right, so what else do we get from this? Well, the point at which sales continue to increase but at a slower rate, this is called, and you might have guessed this from the name, this is called the point of diminishing returns. Point of diminishing returns, which just means, we're still making a profit, we're still getting returns, but it's at a diminishing rate. Hence the name, point of diminishing returns. So what does this give us? Well, the first derivative is positive. The second derivative is less than 0. It's negative, or it's about to switch to negative. And we also know that this occurs at a point of inflection where it changed from positive to negative. So this is where it's just starting to slow down. It's just starting to become negative in the second derivative. So what we actually have here is the point of diminishing returns. It's a point of inflection. Remember our definition for that in 4.1a. That's where the second derivative is equal to 0. It's a point of inflection where it changed from concave up to concave down. It's a very specific type of point of inflection. Point being, when you're dealing with a business question and it asks you for the point of diminishing returns, you're looking for where the revenue, because returns is about your revenue, you're looking for where the revenue has a point of inflection that changes from concave up to concave down, that order specifically. So it's a good thing to keep in mind if you're ever asked to find the point of diminishing returns. All right, so great. What can we do with this? So that covers all of our definitions. So let's go ahead and take an example. Suppose, and I'll leave the second derivative test up here because we're going to use that. So suppose f of x is equal to 4x cubed plus 12x squared minus 180x. Now, the first derivative test, or I'm sorry, the second derivative test tells us we need critical points. In order to get critical points, we have to find, excuse me, we have to find where the first derivative is equal to 0. That's the definition of a critical point. So let's go ahead and do that. So f prime of x is equal to 12x squared plus 24x minus 180. So there's our first derivative. Now, we've got some big numbers here that I don't like. Lucky for us, they're all divisible by 12. So when I set this equal to 0 to find my critical points, I'm just going to divide both sides of the equal sign by 12. So I have here instead x squared plus 2x minus 16 is equal to 0. And so now this is a lot nicer to work with. And if I want to find my, oh, I'm sorry, not 16. This is 15, minus 15. And now to find my critical points, I want to factor this. So let's see, I've got a negative, so I need to have opposite signs. So x plus and an x minus. Factors of 15 that can add or subtract to make 2. Let's see, factors of 15, 5 and 3. In fact, if I do a positive 5 minus 3, that'll give me a positive 2 in the middle. And so we're good. Now we factored it. So what are x values? We have negative 5 and 3. These are our C, the critical points we use for the second derivative test. Okay, great. So we have our candidates. Now we need our second derivative. So f double prime, and be careful here because you don't want to use your version where you factored out the 12. Because we divided it with 0, we can make it disappear. But here it's not equal to 0 anymore, so you don't want to do that. So use the original version we had for the first derivative. So, okay, so what do we get? 12 times 2 is 24. So we got 24x plus 24, derivative of 24x up there. We set that equal to 0 to find our hypercritical points. And we're going to get 24x is equal to negative 24, x equals negative 1. So up above here, we have the critical points. And right here, we have the hypercritical points. And they're both useful to us. So we'll start by, and we'll actually show both lines here, but first we want to use the second derivative test. So that means we need the second derivative line. And label our point, that's a hypercritical point because the second derivative is 0 there. And now just before we test values to the left and right. So if I try 0, f double prime of 0, That's going to be a positive 24. So that's positive. And if I check on the left side, say f double prime of negative 2, that's going to be 48, negative 48, plus a 24, so that's going to be a negative 24. And let's see, did I do that right? Negative 2 times 24 is negative 48. Yeah. So it's negative to the left. Okay, so this is a point of inflection. Now that we know that the concavity changes on both sides, but that's okay. We're not looking for that right now. Point of inflection. I'm just labeling it so you guys know what it looks like. Point of inflection. But specifically, the question is asking us for what are the local max and min using the second derivative test. So the second derivative test says that I need to test my critical points for my second derivative. So when x is 3, that's to the right side over here. That falls in my positive side. So here's 3. And negative 5, that's going to be to the left of negative 1. So that's over here on the left side. It's on the negative side. So what does that tell me? That tells me by the second derivative test, x equals 3 is a local min. Oops. Is a local min. And by the same test, that tells me at x equals negative 5, it's concave down, so it's a local max. And I got that just from the second derivative test. And just double check to make sure it makes sense. You can double check using the first derivative. We had our critical points of negative 5 and 3. If you plug in 0, that's in between. So where's my first derivative? That's up here. 0, 0, negative, that's negative in the middle. If I plug in a 5, well, that's going to get really big. So this is a positive. And if I plug in a negative 6, well, let's see, this is going to be a positive. That's going to be a really big positive, actually. And that's going to be bigger than these other numbers, so it's positive over here. And so by the first derivative test, we have this positive negative at negative 5, so it's a local max, which is what we have here. And at 3, we have a negative positive for the first derivative, which makes it a local min, which is exactly what we have from the second derivative test. So there you go. There's the second derivative test in a nutshell. Let's see, I don't want to push the time too much, so I'm not going to cover all of the examples. But again, if you understood what we did here, then you should be perfectly golden as we move forward. So with that being said, that's everything I have for you today. Of course, if you have any questions, concerns, don't hesitate to email me. We can talk about it. And of course, we have our Q&A coming later in the day, and we can talk more then as well. So that's all I've got for you. With that being said, I wish you the best of luck.